Hello and welcome to this video. In this video, we're going to be looking at the 4 different types of particle interactions that you need to know for A-level physics. Okay, so within particle interactions, we know that things can interact by 4 of the fundamental forces. Right now, the ones that we're going to look at are going to be specific just to the weak nuclear force. All of these particle interactions that we're going to look at in this video are all decays, or are subject to the weak nuclear force. They're not all called decays, but there are 4 of them. So let's take a look. Some of these you might have seen before, some of these will probably be new. So particle interactions, our first one is alpha decay. Okay, so alpha decay. Now you might have remembered this from alpha radiation at GCSE, and essentially an alpha particle is just a helium nucleus. Okay, so it has 2 protons, 2 neutrons, no electrons. This is why it's purely the nucleus. It's not a helium atom isn't emitted, just the nucleus. And what happens is when you have an atom that's way too big, the atom needs to get rid of some of those protons and neutrons because it's becoming unstable. So a massive unstable atom releases an alpha particle to remain stable. Okay, but the process of alpha decay, we have massive particles. This is things like uranium, like radon, like these big particles will just emit alpha decay, and the bigger you get, the more frequently the alpha things will be emitted. We can write these as general equations for interactions. So for example, let's take uranium 92-132, and if that was to decay, it would lose 2 protons, so its atomic number would become 90, and it would lose 4 nucleons since it's emitting this helium, so its nucleon number is going to become 128. This is going to be some element, which I'm going to look up in a second on the periodic table, and then we can plus an alpha, which is just a 2, 4. And this makes the new nucleus that is formed. So as soon as we've changed the number of protons, we've changed the actual element that we have. And this element is actually thorium. Okay, so if we emit an alpha particle, we get thorium left over. Okay, and this is essentially the extent that we need to know for an alpha decay. We're not going to be asked much more than that. So let's move on to beta minus decay. So this is another one that might be familiar to you. So beta minus decay, what we're releasing, so in the alpha decay we released the helium nucleus. In beta decay we're just going to release an electron. Okay, the key is this isn't ionizing something. So if we're releasing an electron, usually if we were to ionize something, we'd release it from the outer shell. What's actually happening in beta decay is the electron is being released from inside the nucleus. Okay, because what's happening in beta decay is that a neutron decays into a proton and releases an electron and also an anti-electron neutrino and an anti-electron neutrino. Okay, so this is the full process. Okay, so a neutron inside the nucleus of this element decays into a proton, releases an electron and an anti-electron neutrino from the nucleus of the atom. Okay, the reason it will do this is because the atom is what we call neutron rich. Okay, and that basically means that it has too many neutrons. and so it needs to get rid of some. And so the neutron, if you remember all the way back to what we looked at, the mass of the neutron, so I'm just going to call this Mn for the mass of the neutron, is 1.675 times 10 to the minus 27 kilograms, whereas the mass of a proton was 1.673 times 10 to the minus 27 kilograms. So because we have this slight difference here, this difference is big enough for us to fit in an electron and an anti-electron neutrino, along with some other just energy that's going to be released from it. And so this is the reason that they include this difference, is so you can understand how a neutron is going to decay into a proton, because a proton is the most stable baryon that we have. So eventually all baryons will decay into a proton, and we're not actually fully certain if a proton is physically capable of decaying. We haven't seen one in all the time that the universe has been, and we predict that if it were to happen, the half-life of a proton would be longer than the age of the universe currently itself anyway. So we're not really sure about that, but that means it's incredibly stable, and so we definitely know protons are the most stable. If we were to flip it and look at leptons, electrons would be the most stable. So let's write an equation for what happens then. So we know we're starting with a neutron and we're ending with a proton plus an electron and plus an anti-electron neutrino. So this is your equation that you can probably just commit to memory. And this is basically telling you what this definition is. So as long as you know one of these things, you can know the other one pretty easily. But they'll sometimes go deeper than this, and they might ask you, instead of just stating this, they might ask you what's happening in terms of quarks. And now what's happening is, in the neutron, we're starting with up, down, down, and we're ending up with up, up, down. So you can see this middle quark has actually changed identity. Okay, so we're changing from a down quark to an up quark. That's releasing an electron and anti-electron neutrino. So this is the quark equation, and this comes up when they ask for the change in quark identity. Okay, now there's a flip side to having beta minus decay. So what if instead of having too many neutrons, this element has too few neutrons? In that case, instead of doing beta minus, it's going to undergo beta plus decay. Now in beta plus decay, we're actually releasing a positron, so the antiparticle of an electron. And what's happening is a proton decays into a neutron, releasing a positron and an electron neutrino. Okay, now some of you might be thinking, you literally just said protons can't decay, and now you're telling us there's a proton decay. Yeah, this beta plus decay only happens inside a nucleus. Okay, so this is not the proton itself decaying, it's decaying because it's part of a nucleus. This is where it starts to get to higher level arguments about this. But if we had a proton by itself, as in not inside a nucleus, not inside anything else, not like attracted to anything, just by itself, it will have a very, very long half-life. If we have it as part of a nucleus, because the whole nucleus is unstable, the proton basically says, okay, and then the proton decays for the benefit of the whole nucleus. So it's less the proton itself decaying, it's more the nucleus as a whole decays, just to clear that up. But we can write an equation for this, so it becomes a proton decays into a neutron plus a positron and an electron neutrino. Notice the difference. This is an electron neutrino, not an anti-electron neutrino, and we're going to see why this is the case when we look at conserving quantum values in another video. But we can also go a bit deeper with these, and we can say, well, this is a proton, So it's going from an up quark to a down quark plus all the other stuff in the equation. And this is beta plus decay. Okay, so it's basically the direct opposite of beta minus decay. And the last one that we're going to go through is called electron capture. Okay, now electron capture is going to release just an electron neutrino. Okay, so it's a massless particle. Okay, so this is kind of a weird thing to happen. So what electron capture is, where in all the rest of them it's been something that's spontaneously decayed because something is unstable, electron capture is because something is unstable, the atom as a whole wants to make it stable again, and so it will do things that we would see as originally not acceptable, but we know it happens because we can't argue with experimental evidence. So electron capture is where, if we have a electron, so the electron in the innermost energy level, what happens to it is it's essentially attracted to the protons in the nucleus, so is pulled into the nucleus by the electromagnetic force. So that's what's going to start this off, but what happens after that is then due to the weak force. So when it's pulled into the nucleus, it's going to come to a proton, because that's why it's attracted there, and it fuses with a proton. Fuse is probably not a great word. It binds with a proton in order to, or combines with a proton in order to form a neutron. Okay, so the electron in the innermost energy level is pulled into the nucleus and combines, or is absorbed into the proton even, combined with proton to form a neutron and release an electron neutrino. Okay, so we're starting with a proton plus an electron, because the proton is dragging in this electron, and then these are going to come together to form a neutron and release an electron neutrino. So these are the four interactions that you have to be familiar with. You'll have to know each of these equations for each of these and a general description of them. I would personally recommend just learning the equations for each of them, because from the equations you can work backwards and figure out what the wordy stuff is. So if you just remember what the equations are, it will help you out a lot. But these are the four types of interactions. I'm now going to do a video looking at how we draw a Feynman diagram for each of these, so stick around for that.